So in this example, we are given the technology matrix or the input coefficient matrix, which is denoted by A, and we have to find the level of output, which is X, vector X, if the final demand is 20, 0 and 100. Okay, so a vector means if it has only one column, it's a column vector. If it has only one row, it's called a row vector. So usually X level of output is it's a column vector. Okay, so again, as we've shown in the previous videos, how do we find the correct level of output to satisfy intermediate demand and final demand? X, and we have derived the formula, X is equal to identity matrix minus the input coefficient matrix, inverse of that, multiply the final demand vector. So to solve this is easy. We just have to remember the steps. The first of these steps involve, okay, you find the determinant, that is, you find I minus A. Okay, for the first step is to subtract the input coefficient matrix, which is your A, from the identity matrix. Okay, and then you find the determinant. And if you should remember that A here is a 3 by 3 matrix. Why? Because there are 3 rows and 3 columns. So your identity matrix should also be a 3 by 3 matrix. It should also have a 3 rows, 3 columns. Now if A was, let's say, a 2 by 2 matrix, okay, if you're working with 2 by 2 matrix, your identity matrix should also be a 2 by 2 matrix. Okay, so once we've taken care of that, now we can subtract, okay, the input output coefficients from the values of the input output matrix, or from the values of the identity matrix. So after subtracting, okay, we have to find the determinant. Now in finding the determinant, okay, remember, you can use, in finding the determinant, what we're doing here is we're using 0.9 minus 0.3 and minus 0.1. So you can use any 3 elements of a row or a column, okay, but they must be of the same row, they must be of the same column. Okay, the determinant remains the same. So what we're basically doing here, if we take 0.9, okay, we are multiplying 0.9 with its minor. Okay, now what is a minor? What is a minor? Now a minor is nothing but a subdeterminant. And how do you find the subdeterminant? So the elements which are left out after deleting the row and column where you find 0.9, those are called the minors or the subdeterminant of that element. So if you look here, let me use a different color. If you look here, 0.9, okay, these are the row elements, okay, which fall under the same row as 0.9, and these are the column elements which fall under the same column as 0.9. So these elements which lie over here, okay, these are called the subdeterminants or minors of 0.9. So this is how you find the minors, and you multiply that element or the element with the minors. Okay, so here by removing because here 0.9 lies in the first row and first column, so if you remove elements in the first row and first column, your minors or the subdeterminants are 0.8 minus 0.2, 0.7. Similarly, if you're using minus 0.3, okay, and minus 0.3 falls under the second row and the first column. So you remove the elements in the second row and in the second column and the first row. The elements left are called the minors, and if you cross multiply these elements, you get a subdeterminant, and then you multiply it with minus 0.3. okay, So these are the minors of minus 0.3. Now you might wonder, why is there a minus sign over here? You should remember that the elements, okay, of a matrix are also positional elements, which means if it's a 3 by 3 matrix, these are the signs associated with each element. And how do we derive these signs? If you look here, these are the columns, okay, so these are your row, your first row, your second row, your third row, your first column, second column, third column. So 0.9, what will be the positional value of 0.9? Now if you notice here that 0.9 belongs to the first row and first column, and if we add these two values you get 2, which is an even number, hence it'll take a positive sign. So here it means nothing's written, but it means that there's a positive sign. Now if we look at minus 0.3, now minus 0.3 is an element of the first row and the second column, and if we add 1 plus 2, first row, second column, if you add the numerical values of those positions, you get 3, which is an odd number, hence we give a negative sign, or the value will be preceded by a negative sign, or a negative sign will be written before this value, so hence we have a negative sign. Then minus 0.1 here is an element of the first row and the third column. So first row and third column, and if we add these numerical values, you get 4, which is a positive, which is an even number, so a positive sign will be written before this element, which is minus 0.1, and we know that plus into minus is minus, so it remains the same. Hence that is how we get the minus sign over here. And if we work that out, what we get is what we get is 0.504, which is the determinant of matrix 1 minus identity matrix minus the input coefficient matrix. So step 1 is done. Step 2 is to find the cofactor matrix of I minus A. So that is step number 2. Find the cofactor matrix of I minus A. So here again, the concept of minors and cofactors become important. Now cofactor is nothing but minus with a sign. Okay, so again we go back to that concept of each element having a positional value depending upon the column number, the row number. Okay, these are the positional signs, or the positional signs for each element. So 0.9, if you remember, is an element of the first row, first column, and if we add 1 plus 1, we get 2, which is a positive, which is an even number, so hence there's a positive sign, which means it will be preceded by a positive sign. So a cofactor is nothing but a minor which is preceded by a sign, or when a sign is placed before the minors of each element, then that is called the cofactor of that element. So the cofactor of 0.9 is equal to plus the minors, okay, then you cross multiply, which is 0.56, and 0.56 is the cofactor of 0.9, and 0.9 is an element of the first row, first column. So when you write the cofactor matrix also, 0.56, okay, should be in the first row and first column. Now the second element here, the cofactor of minus 0.3, and if you remember, minus 0.3 is an element of the first row and second column. So if we add 1 plus 2, the numerical values 1 plus 2, we get 3, which is an even number. So hence we will have a negative sign, and that negative sign will be written before the minors of this element. And again, what are minors? The elements which are left after deleting the row and column where this element is found. So we know here that 0.3 is found in the minus 0.3 is found in the second column, first row. So if we remove these elements, we are left with these. Okay, those are called the minors, and based on the position of minus 0.3, because if we add the row and column number, we get an odd value which is equal to 3. So hence this will be preceded by a negative sign. So same way, okay, we just have to remember the positional signs that will be used depending upon the row position, column position. If it's an even number, we will have a positive sign. If there's nothing here, it means there's a positive sign. And if it's an odd number, we have a negative sign. And how do we find the minors? Just remove the elements which fall under the same row and column as that element, and the elements left will be the minors of that element. So now here we find that the cofactor of minus 0.3 is 0, and since minus 0.3 it belongs to the second column and the first row, so 0 also will be placed in the position of minus 0.3. so that is how we get 0. So it's the same for all values. Okay, what is important is you have to remember the positional signs, okay, because these signs plus minus, they will be placed before the minors, okay, or the subdeterminants of each element, and if you make a mistake in that, it can alter the values. So what we've done here is we have found the cofactor of each element, and we have substituted these, or we have placed these values according to the position of each element. So, and that is how we form a cofactor matrix. So lastly, we have 0.7. The positional value, it belongs to the third row and third column. So 3 plus 3 is 6, which is an even number. So we will have a positive sign placed before the minors of 0.7. And what are the minors of 0.7? So if 0.7 belongs to the third row and the third column. So if you remove the third row and third column, you are left with these values: 0.9, minus 0.3, minus 0.8, and 0. So you cross multiply, you find the subdeterminants, which will be the cofactor, okay, and you get 0.72. And since 0.7 is element of third row and third column, so even 0.72 will be placed accordingly. Now next step is to find the adjoint matrix of one of identity matrix minus the input coefficient matrix. Okay, and the adjoint is nothing but the transpose of the cofactor matrix. Transpose means you interchange the rows and columns. So if you look here, for this cofactor matrix, okay, so the adjoint matrix is nothing but the transpose of cofactor matrix, okay, which means you interchange rows and columns, which means columns become rows and rows become columns. So if you look here, these are your columns, right? Let's say for the first row, these are your rows. So if you look here in the adjoint matrix, they become your columns. Similarly, the second row, these are the elements of the second row, they become columns. So 0.21, 0.63, 0, so on, so forth. Then we find the inverse, and if you remember the formula of the inverse of any matrix, the inverse of any matrix, the matrix A, is nothing but the adjoint matrix of A divided by the determinant of A. And we've already found what is the adjoint here, so it means the inverse of this, okay, is nothing but the adjoint of matrix I minus A divided by the by the determinant of I minus A, and I minus A is nothing but, when we found, it is 0.504, and that this is your adjoint matrix, which is the transpose of the cofactor matrix. And by question, your final demand vector is 20, 0 and 100. Okay, so using the formula given by the input output model to find X, so what we do first is we multiply, okay, this matrix with this matrix. Okay, so what we're doing here is we are multiplying this matrix with this matrix. So these are your rows and these are your columns. So if you look at this first matrix, it has 3 rows, 3 columns, and the second matrix has 3 rows and 1 column. And for matrix multiplication, the column number of the first matrix and the row number of the second matrix should be equal. And when they get multiplied, the answer or resulting matrix should have the row number of the first matrix, the column number of the second matrix. Okay, so if we multiply, you get this matrix over here, and this has 3 rows, 1 column. Okay, so that is the basic rules of matrix multiplication. So what we're doing here is we're multiplying each row element with each column element. Okay, so we go on adding. So the first row with these column elements, then the second row multiplied with these column elements, and then the last row multiplied with the column elements. So after we get a 3 into 1 matrix, which should be your matrix based on this equality. Okay, so next what we do is we simply divide each value by the determinant of I minus A, and that is how you get your X vector or production matrix. So where 50 will be the product, let's say, of sector 1 or of good 1, 35.71 will be the output of good 2 or sector 2, and 142.86 will be the output of third sector or the third good. So that is how we find the correct value of levels of output to satisfy intermediate demand and final demand.